Welcome back. In today's lecture, I am going to talk about energy based modeling. Okay, so what we found in the previous class that whenever I have some system, it is possible to show that if I formulate some kind of Lagrangian kind of things, okay, and for mechanical system or some kind of electromechanical system, that particular Lagrangian is nothing but difference of kinetic energy minus potential energy, then I can able to get the dynamics of the system in form of the differential equation. Okay, so let us try to see one motivating example. Okay, so in order to motivate the formulation of the energy based modeling, what I have done, I have actually taken very simple system. Okay, here you can see that here I have one mass. Okay, and actually this system is just moving in one direction. Okay, so whenever I have some mass, so I have applied some force, and this downward force is force due to gravity. Okay, and after that I have, suppose I have to write the mathematical model of this system. I have already told you that whenever we are writing mathematical model, we are doing several assumptions. So first assumption we have to do, we have to assume that all masses are concentrated at certain point. Okay, that we have given certain name, that center of mass, and after that whatever force g, I am assuming that that is constant. Okay, and after that, for simplicity, I am assuming that this mass is just moving either vertically upward direction or downward direction. Okay, and this is also called degree of freedom, so they have just 1 degree of freedom. Okay, so since situation is very simple, and due to that reason I can able to apply the modeling by first principle. Okay, and what modeling by principle is suggesting us that you can identify all different kind of forces, and after that you can just apply the second law of Newton. Okay, so if you apply the second law of Newton, then I can able to write my double dot equal to F minus mg. Okay, so force F is acting vertically upward direction and mg in the downward direction. Okay, and I am assuming that y is completely differentiable because this is moving in a straight line, so I can assume that. Okay, now let us try to notice something from this particular equation. What we have noticed, that the left hand side of this particular differential equation, this is second order differential equation, so I can also able to write my double dot as a d by dt my dot. I am assuming that mass is constant. Okay, now I can also able to rewrite this like d by dt, and dou by dou y means partial derivative of this whole term half my y dot square with respect to y. If I write, then still I will able to obtain this thing. Okay, so these two things are equivalent. Either I can write like this or this. I hope that you all are actually agree with me. And after that, now what I am telling, that I am going to give some name to this, and we all are actually well aware that is nothing but the kinetic energy of the system. Okay, so I have used some terminology for that, that is Ke, kinetic energy. Okay, and now likewise I can also able to write mg. Okay, and mg is nothing but that is gravitational force, like dou by dou y mgy. Okay, so now what happens, that I can give certain name to this as a potential energy. Okay, after that what I am going to do, I am going to define L as a kinetic energy minus potential energy. So if you define kinetic energy minus potential energy, so I can write kinetic energy as a half my dot square minus mgy. Okay, so from here what we get, that if I will take partial derivative of L, L is also called Lagrangian. Okay, Lagrangian means kinetic energy minus potential energy. And in previous class we have seen that whenever some dynamical system is moving, at that time what they are doing, they are trying to extremize the integral of Lagrangian between some time interval t0 to t. Okay, so I have defined similar kind of things, and after that I am going to take the partial derivative of L with respect to y dot, then I will get this. Okay, now finally what I am going to do, I am going to derive same kind of equation like Newton's. So Newton has actually, based on the first principle, modeling by first principle, what we found that my double dot. Okay, so if you take just partial derivative of L with respect to y dot, then I will get my. So I have to take one more time derivative dy dt, then I will get y double dot. And due to that reason, I have written like this. Okay, so what happens that I have two terms. If you see this equation carefully, so in Newton's law, this term is due to motion, my double dot, and this is due to the position. You can tell mg is actually force due to gravity. So this term is responsible for kinetic energy, this term is responsible for potential energy, and this is some external force. So one can also write this whole things like this. Okay, and this equation is nothing but Euler-Lagrange equation. Okay, in this way I can tell that there exists some kind of equivalence between Newton's equation to Euler-Lagrange equation. If you see this simple example, then one can just tell that actually Euler-Lagrange equation is nothing but some kind of interpretation in terms of energy. Energy means kinetic energy minus potential energy. Okay, and after that it means that it looks like that this equation comes from the Newton's law, but that is not the case. Actually, whenever we are trying to formulate some kind of differential equation, then we are doing exactly reverse process. Okay, so any Newton's equation can be formulated from this. Okay, sometimes it is possible to show that you are not able to formulate, okay, or very complicated formulation occur whenever you are just relying on Newton's law. Okay, but Euler-Lagrange is independent of any coordinate system. You can select any coordinate system. Okay, polar coordinate system, whatever, a spherical coordinate system, whatever you want, you can select it, and after that just you have to identify the kinetic energy or some kind of quantity like kinetic energy, and now you can do reverse process. So here, for motivation, what I have done, I have started with the Newton equation, and after that I land up to the Lagrange equation. But fundamental is that you can start from this equation. Okay, and how to start? You can define L. L is called Lagrangian, and what is meaning of Lagrangian? That is difference of kinetic energy minus potential energy. And after that you can solve this partial differential equation. Then what happens, that you are able to get the differential equation, and that differential equation is the mathematical model of that physical system. Okay, and in the previous class we have already gone through the Hamilton principle of least square. Okay, so I will also discuss one more method of modeling in the next class, that is Hamiltonian based modeling, and at that time I will tell you that what is the difference between Lagrangian based modeling and Hamiltonian based modeling. So even if Lagrangian modeling is based on the Hamilton principle only, and I have already told you that Lagrangian and Hamiltonian means Euler or Hamiltonian or Lagrangian, all are from the same lab. Okay, so what Hamilton principle are stating, of all possible path along which a dynamical system we have already defined, that I have some kind of object. If I give real data, then I will get the real data output as a real data, that is called dynamical system. And we have also seen that whatever output, that should be not function means whatever input that is not function of the previous or future output, that kind of things we have seen. Okay, so of all possible path along which a dynamical system move from one point to another point in configuration space, we have already now talked about the space, so I am not going to define again. Within a specified time interval means subset of the real number, the actual path followed is which minimize the time integral of Lagrangian function. Okay, so actually Hamilton principle is telling extremize, and it is possible to say to show that basically whenever some system is moving, they are trying to minimize T0 to Tf. They are actually minimizing, not extremizing, but also the minimizing this Lagrangian. And here Lagrangian can be defined as a kinetic energy minus potential energy. Okay, and you can define this as a something phi t. Okay, now based on this particular observation, we are trying to develop some kind of mathematical model for the system. Okay, so I am going to start with very simple system. Okay, so first system, you can see here that I have taken mass. Okay, and this mass is moving in one direction. Okay, so one very important idea of modeling here, that you can see that in the previous example what we found, that whenever we have 1 degree of freedom, at that time we are solving one set of partial differential equation. Okay, so here y is called the generalized coordinate. Okay, and I have told you that any generalized coordinate you can select, but actually number of generalized coordinate is equal to degree of freedom. Okay, so let us try to see that here what is degree of freedom of this particular system. So this system is only able to move in this particular direction. Okay, in one direction. So due to that reason, one general coordinate frame is okay. Okay, with respect to that general coordinate frame, you can formulate the Lagrangian equation. You are able to understand this concept in another problem when I will do where more than one general coordinate system is involved. Okay, so what I am going to do here, I have just this system M, and this is a spring, this is a spring constant. So X is actually some kind of displacement occur here X. I am assuming there is no external force. Okay, so if there is no external force, then simply this is basically external force. So I have to keep that external force equal to 0. If that external force come into picture, then I have to equate with that external force. Please be careful here, whatever external force that is acting along this coordinate system. Okay, so y is just coordinate system in vertically downward direction, so that force only I have to account. There is no need to account the any horizontal force. So I have to just see the force associated with the general coordinate system. Okay, so here there is no force associated, external force associated with this general coordinate system, and due to that reason means right hand side of the Euler-Lagrange equation that equal to 0. So kinetic energy, you all are already knowing this fact that whenever some system is moving, at that time I can able to define kinetic energy, and kinetic energy is nothing but the half mx dot square. Okay, and how to define V? V here I have represented as a potential energy. So V is half kx square. Okay, and just now you have to solve the Euler-Lagrange equation. Okay, and after that you will get same equation like the Newton's law. If you apply Newton's law, then you will get this equation. So same equation I will get here also. Okay, now let us come to the little more complicated system. So this system is very simple. Now what I have done, this mass spring damper system. Okay, so those who are actually done course on the linear control theory, you might have seen that in every linear control theory book this example is very famous. Okay, so again I am going to do the mathematical modeling for that. Okay, so I have already told you that whenever you are going to do the mathematical modeling based on the energy way, then first you have to identify the general coordinate system. Okay, so try to identify the general coordinate system. So what this mass is doing, they are moving in the upward direction or downward direction. So again they have just 1 degree of freedom here. And what kind of external force is acting along this coordinate system? That is Ft. So external force now that actually shown here, that is basically nothing but the Ft. Okay, and here from here to here, this distance is h, and xt, I am assuming that I have displaced this mass by xt. Okay, now try to identify all kind of kinetic energy or their equivalence also you have to identify. Okay, so you can see here that what happens, that whenever this mass is moving, so due to rate of change of x, since h I am assuming some constant number, so basically x dot, due to x dot, basically kinetic energy comes into picture. So I have written like this. Okay, if you see carefully, one more part of kinetic energy that comes into picture. Okay, so could you please identify, anyone, could you please identify that where kinetic energy kind of quantity comes into picture? If you see a spring, so obviously a spring has some kind of energy that is in form of potential. Okay, that is half kx square. Okay, if you check here that in this damper, okay, so inside damper force is generated whenever there exists some kind of motion. Okay, without motion there is no force, because if you see bx dot is bx dot. Okay, so if you see the damping force. Okay, so here again x dot kind of things is involved, so you can interpret that as a in form of kinetic energy only. Okay, but most of time people are writing that kind of dissipative term separately. Okay, so either you can account here means half mx square plus half bx dot square. So you can able to define this as a total kinetic energy. Okay, kt, or you can separately define. Here I have defined separately. Okay, still formulation remains the same. Okay, and how to define the kinetic energy? So potential energy. So potential energy, one potential energy in the spring, that is half kx square, and after that due to the gravity I have mg h plus x. Okay, and due to that reason, now this is the form of potential energy. And again you can, what you can do, you can define the L equal to means kinetic energy minus potential energy. Okay, I have already told you that sometimes people are separating this term of kinetic energy which is dissipative in nature. Okay, and for that they are just adding dou p by dou x in this equation. Okay, so whenever some can, so try to understand like that. So here one more thing I want to clear here. Actually addition is not possible because d by dt comes into picture, so you have to remove this. Okay, because I have to calculate force. So if I will try to capture force, because somehow what I have to do whenever I am applying the Newton's law, at that time I have to do the rate of change of momentum equal to force. Okay, so force kind of quantity I have to take. So in order to collect force kind of quantity from here, I have to take just partial derivative with respect to x. Due to that reason separation is required. Okay, so whatever things I have told, that is wrong. Okay, you cannot able to add here potential energy kind of quantity, just you have to separate it. Okay, and what you have to do, you have to add or subtract this quantity along with the force, external force. Okay, so force part you can add or subtract here, not kinetic energy part. Okay, so again please come here. So we are trying to identify all kind of kinetic energy. So kinetic energy is half mx square, potential energy is kx square mgx, and after that we will try to identify some kind of dissipative force. Okay, so principle is exactly like the non-inertial frame. Okay, so whenever we have certain kind of non-inertial frame in Newton's law, what basically we are doing, we are applying some kind of opposite kind of force. So similar kind of things basically we are doing here. You can see that external force is Ft, so we have to subtract that much of force. So dou P by dou X, that is subtracted here. Okay, so now I hope that you are able to understand the idea, that now what I have to do, I have to take the d by dt, dou L by dou X, and dou by dou X, and all dissipative term we have to add. Okay, sometimes people are also telling as a Rayleigh function, this as a Rayleigh function people are giving name. Okay, but there is no need to complicate thing. Just you can tell that, try to identify those kind of term which is responsible for dissipation, because whenever we have mass spring damper system, so energy is dissipated with respect to damper. Okay, so I will identify that kind of term. Okay, and after that what I will do, again I will substitute everything and I will get second order mathematical model, and try to now verify from the Newton's law, you will get the same mathematical model. Okay, but here you can see that there is no need to worry about that that how much force is acting. Just you have to identify that in which direction, means in generalized coordinate direction which force is acting, that much you have to worry. Okay, now let us come to the next example. So next example I have taken RLC circuit. Okay, so again here what I will do, I will try to identify the kinetic energy, I will try to identify the potential energy, I will try to identify the some kind of dissipation that occur, so I have to identify. Okay, so if you try to identify that, here you try to see that this ut is responsible for external force. Okay, and after that I have resistor, so energy is going to dissipate across resistor. Okay, so I have to identify that, and after that capacitor is going to store energy in form of potential energy, and inductor is going to store energy in form of kinetic energy. Okay, so even if that is electrical system, but I am going to use the concept of same kind of theory like the mechanics only. Okay, equivalence, from the equivalence. So what I am going to do here, you can see here that kinetic energy here, that is half L q dot square, potential energy q square by 2c, and here again dissipative term half r q dot square I have written here, and finally what I have to do, whatever forcing function, from that I have to subtract this term dou p by dou q dot. Okay, here try to see that generalized coordinate, again here if you see carefully, then I have just one coordinate system, so I have to select coordinate system either as a qt or you can select as a it. Okay, so for simplicity I have selected qt, but you can select it also, that doesn't matter. Okay, and in terms of q, that general coordinate system, basically I am going to write the equation. Okay, and finally you can see that same equation comes into picture. I hope that most of you are already done course on the electrical engineering, and at that time you might have seen that this kind of equation basically comes into picture, that and this is voltage across the capacitor, and after that this is u. So same kind of equation I can actually recover by applying, either you can apply KVL or you can apply the Euler-Lagrange formulation. Okay, so just three things you have to identify. That first important thing, that general coordinate system, second kinetic energy, potential energy, and try to identify where dissipation is going to occur. Okay, now let us come to the some realistic system. So this is one of the real system, that is capacitor macrophone. Okay, so whatever macrophone we are using, okay, that is nothing but some kind of electromechanical system. Okay, so how basically that is working, we have some kind of variable capacitance here, and whenever we are speaking here, then actually the distance between two plates is going to change, and since distance between these two plates is going to change, and that is actually responsible for the variation of voltage. Okay, so in this way, now suppose I have to do the mathematical model of this system. So here I have two different subsystem is involved. One is electrical system, another is mechanical system. Okay, so if you see electrical system, so electrical system contain RLC, mechanical system is containing mass spring damper. Okay, now this plate is fixed and this plate is actually moving. Okay, so you know that whenever I have to calculate capacitance, that is capacitance equal to A epsilon 0 by D, and here D is changing. Okay, this is actually this plate can move, and due to that reason C can changing, and whenever C is changing, then voltage is also changing. That is the principle. Okay, so here now only one general coordinate system is not enough. Okay, because this plate is moving in this direction, so actually I have to select one generalized coordinate system, that is the displacement x. Another thing, that whenever, since capacitance is changing, so either current is generated or charge is going to vary, and due to that reason I can select another coordinate system as a charge or current. Okay, so I have selected q here, so I have two different general coordinate system. Okay, and now I have to identify the kinetic energy. Okay, so total kinetic energy I have to just identify. So you can see here that kinetic energy is stored here in two different way. One kinetic energy is stored inside this inductor, and another due to this motion. Okay, and due to that reason I have two different terms here. First term is half L q dot square. L is the inductance, and after that this plate has some mass, and I am assuming that the mass of that place that plate is m. Okay, moving plate, I am assuming that they have some mass. Okay, so this plate has mass m. Okay, and due to that reason I have here half mx dot square. Okay, and after that I have to identify the kinetic energy. So kinetic energy, potential energy. So potential energy is going to store inside this spring, and as well as this capacitor. Okay, and if you write that, then q square by 2c, these kind of things you have already learned during your school time. Okay, now capacitance C is A epsilon D. D here initially I am assuming x0 is the equilibrium length, and whenever we are going to speak something, then actually what happens that some difference comes into picture, and due to that reason this displacement occur, and that I am going to represent by x, and due to that reason x0 minus x I have written here. And after that what I am going to do, I am going to again define the potential, or substituting C I have defined the total potential energy. Okay, now I have to identify third quantity, that is dissipation. Okay, so dissipation actually occur at two different places, at this damper and across this resistor. Okay, so same kind of things basically I have written here, that P equal to half RQ dot square and half B X dot square. Okay, now what we have to do, we have to formulate the Lagrangian. So how to formulate the Lagrangian? That is kinetic energy minus potential energy. Okay, and after that now I have to write the Lagrangian equation. So here you can see that two generalized coordinate is there, and due to that reason I have two different Euler-Lagrange equation. Okay, and I have to also identify the force along that generalized coordinate system. So you can see that one mechanical system has force Ft. Okay, and after that now if you see this electrical system, then they have some kind of force, and that force I have written as a U or V, voltage. Okay, and due to that reason what I have done, first time I will take the partial derivative of Lagrangian with respect to x and x dot. Okay, and after that I will formulate this equation. I hope that you can able to do that. That is not very easy, very difficult. D by dt dou L by dou x dot you have to solve, and after that dou L by dou x, and after that you have to add one more term, that is dissipative term. So dou P by dou x dot, and after that equal to force along this. So x I am telling due to F. So if you solve it, then you will end up with this equation. Okay, in place of x dot, now you can just replace by q in q dot. So if you replace this by q dot, x by q, and x dot by q dot, again you will get the second equation and f by v. Okay, in this way quickly you are able to get the two set of differential equation, and both set has second order, and due to that reason this practical system, that is capacitor macrophone, that is actually represented by fourth order differential equation. Okay, so now let us come to the again third system, that is robotics. Okay, and I have already told you that nowadays means branch of robotics is very much important. Anyone has confusion, then please let me know. Anyone has confusion? Okay, so now I am going to come to the fifth example, and here again I have collected some example from the real system, that robotic system. Okay, and suppose now that I have some kind of robot that can able to do two kind of motion. Okay, so they can do rectilinear motion along this. Okay, so this is flexible. Okay, so this can move in this direction, means upward direction and downward direction, and they can also rotate. Okay, so here now try to see that I have 2 degree of freedom. Okay, 1 degree of freedom because I can able to rotate. So in order to rotate I need some rotation angle theta t. So I have to formulate one Euler-Lagrange equation with respect to theta t. Okay, and after that I have also some kind of rectilinear motion along this length. Okay, and that coordinate system I have selected rt. Okay, and what I am going to do now, using these two coordinate system, generalized coordinate system r and theta, I am going to write the differential equation, Euler-Lagrange equation. Okay, so I have already told you that you have to just identify force along that particular generalized coordinate. Okay, so if you see the generalized coordinate theta, so how basically theta comes into picture? Whenever some torque is going to act. Okay, so some kind of torquing function, when that is going to act, then one equation that comes into picture. Okay, so Ankit, do you have any confusion? I found that Ankit has raised his hand. Ankit, do you have any question? Ankit, are you here? Could you please mute yourself if you don't have any question? Ankit? Okay. Now here you can see that if you see this coordinate system theta t. Okay, so we have one force I have to identify, that is nothing but torque, and in this direction I have force F. Okay, and same kind of things basically I have written here. Okay, now what I have to do after that, just I have to formulate the expression of kinetic energy and potential energy. Okay, so in order to find the equation of kinetic energy, you can see that two different kind of motion is there. One is rectilinear motion. Okay, so that is pretty easy to calculate the kinetic energy, half m is the mass of the bob. Okay, I am assuming here that whatever mass of this particular rod, that is negligible. That kind of assumption I have. Okay, but suppose if rt has mass, then you have to think some one more component you have to add. Okay, now what what kind of kinetic energy that comes into picture? R dot square. And after that, since I have rotation also, so whenever we are trying to calculate the some kind of kinetic energy due to rotation, then in place of mass I have to replace by moment of inertia, and due to that reason I have actually replaced by inertia mr square. Okay, I hope that these kind of things is very much primitive. Okay, and after that now I have to calculate the potential energy. So potential energy means distance from here we have to calculate. So I have to calculate the projection of this along this. Okay, and that is nothing but r sin theta. Okay, so mg r sin theta comes into picture. Now I have to also identify some kind of dissipation term. Okay, so two kind of dissipation that occur. One dissipation, since this length is changing, and due to that reason some kind of friction force is also generated. Okay, something is rotating, again some kind of friction force is actually comes into picture, and due to that reason, one due to theta dot and another due to r dot, because whenever we have seen that whenever dissipation force comes into picture, that is due to rate of change only, and that I have basically identified. Now you can easily you can able to do, you can formulate the Lagrangian by kinetic energy minus potential energy. Okay, and now what you can do, you can calculate three things: dl by dq, dl by dq, dp by dq dot, and after that equate, put inside the Euler-Lagrange equation and equate with the generalized force acting and their individual direction. So one direction I have two coordinate system, one coordinate system I have selected theta, another is r. So you have to just equate that, and in this way I can able to get this equation. Okay, so if you go via the uh, Newton's way, you are able to get same equation. Okay, but driving this equation is not so straightforward. But using this, now even if I have some kind of system where suppose that here I have just one link, in several places if you see the physical manipulator, they might have more than one place, they might have of this shape also. Okay, sometimes we have more than one joint, these kind of things. Also you are able to do same kind of things and able to calculate the differential equation governing this system. Okay, so actually I have to remove the Ankit because I think that he's just doing time pass, so I have to remove him. Remove. Okay, now and so in this way I can able to get the Lagrange equation, and it is possible to show that whenever you will do any mathematical model of robotics, okay, this kind of common differential equation comes into picture, same like this. Okay, like this. And if you see the robotics, then in robotics mq is nothing but the inertia matrix, this vqq dot is this centripetal force, and jq is the gravity vector, and q is the input vector. Okay, so like that if we have more degree of freedom, again we will get very simple equation. So those who are working in the direction of robotics, those who are working more than one system or integration of more than one system, what is my suggestion, please go through the energy based modeling or Lagrangian modeling. Okay, so here I have again fourth order differential equation. Okay, but here please be careful whenever you have to talk state space representation. So again you have to represent this fourth order differential equation with the set of first order differential equation. And in next class I will show you that if you use the another formulation that is called Hamiltonian formulation, then directly you are able to get the mathematical model based on the first order differential equation. Okay, so Euler-Lagrange equation whenever you are using, then you can able to get several connected differential equation and all have order second. Okay, and finally whole system is the integration, means generalized coordinate you have to select with respect to each generalized coordinate or degree of freedom, you have second order equation. So suppose if you have four degree of freedom, then you have four set of two second order differential equation, means total order of the system is 8th. Okay, now let us come to the another means the modeling based on Euler-Lagrange equation. So during your first year course you have already seen that if you have certain connection of capacitor, resistor, inductor, then you are actually writing equation based on KVL and KCL. Here directly you can able to get. Okay, just what you have to do, you have to identify the general coordinate. So general coordinate you can select as a charge, and after that you have to select the forcing function along the general coordinate system. So here I have two mesh electrical circuit. So what I have done, I have selected one general coordinate system as a q1 for this, and Q2 for this. Okay, and after that we know that this is resistor, so that is responsible for dissipation. So I will calculate the dissipative force. Okay, capacitor is responsible for potential energy and inductor is responsible for kinetic energy. Okay, so what you can do now, you can write the kinetic energy, you can write the potential energy, same kind of things I have done. So please do by yourself now. Okay, because now everything is just a calculation. Okay, not much thing is involved, and from here you are easily able to guess that the this whole circuit is represented by fourth order differential equation again, because I have two independent coordinate system q1 and q2. Okay, now similar way, even if you have another complicated circuit, okay, you are able to write the differential equation. So again, this circuit I have left for your home assignment. Okay, what you can do, again you can select the coordinate system, you can formulate the kinetic energy, you can formulate the potential energy, you can formulate the dissipation term, and after that you can write the differential equation. Okay, so in this way finally I have written the differential equation like this. Okay, so these are very easy thing. Okay, so now it is time to conclude the today's lecture. So what we have done in today's lecture, in the previous lecture we have already seen that how to come up with the Euler-Lagrange equation. Okay, and what kind of principle is involved there. We found that whenever some system is moving or dynamical system is moving from one point to another point, okay, that is nothing but, you can think that means dynamical system is evolving, means the state are changing with respect to time. At that time they are trying to minimize some extremize some kind of action function. Okay, and that action function is nothing but the Lagrangian. Okay, now whenever suppose that if system do not have any dissipative term, okay, then equation is very simple. If we have dissipative term, then we have to do some certain kind of modification, or some external force act on the system, then we have to do modification. So what kind of modification we have to do? Okay, sometime that is also called the Alembert principle. Okay, so what we have to do, we have to calculate the kinetic energy minus potential energy Lagrangian, and we have to write the partial derivative with respect to coordinate, general coordinate, and rate of or rate of change of with respect to rate of general coordinate. Okay, and after that we have to do some extra work. What kind of extra work? We have to identify the dissipative function, and after that we have to take the dissipative function partial derivative of different dissipative function with respect to x dot, because whenever some dissipation occur, at that time that is occur only due to rate of change. Okay, and after that we will write the whole system of equation. Okay, so in this way, using this principle, you are able to write very complicated. Suppose that nowadays I have already told you that whenever you are talking about electrical vehicle, whenever you are talking about robotics, whenever you are talking about network system, power systems, at that time you have to integrate several components. Okay, now during integration what we found that just we have to check that what is general coordinate involved. Suppose you have one mechanical system, one chemical system, one electrical system, and you have to integrate all three. Okay, so try to write the differential equation or Euler-Lagrange equation for each and every subsystem, and just please write it. Okay, and what you have to identify, the force along first subsystem, force along second subsystem, force along third subsystem. So individually you have to equate that, and after that what you have to do, you have to check that what kind of kinetic energy that is actually associated with each and every system. You have to add all. What kind of potential energy, you have to add all, and after that you have to just solve the partial differential equation, and after solving that you are able to get the second order differential equation. Okay, so if you see second order differential equation, sometime this second order differential equation is linear, sometime that is not a linear. Okay, that might be we have already seen the category autonomous system, non-autonomous system, force system. So it is possible to show that For more complicated system, solution of differential equation might be non-linear time varying differential equation, non-linear force time varying differential equation. Okay, so in this way I can able to do mathematical model of any complicated system. Okay, so lecture is in from my side. If you have any question, then please let me know. So one more lecture I will take, and then I will complete the energy based model. Okay, so what we have seen there, that energy based modeling is actually inspired from the variational calculus. Okay, modeling by first principle is actually inspired from the classical calculus. Okay, so suppose that now people are moving towards the quantum mechanics. Okay, so it is possible to show that even if quantum mechanics means some kind of laser, and using laser we try to develop some kind of technology, it is possible to show that again I can use the variational calculus, because I have told you that variational calculus is consistent in each and every scale. Okay, but Newton's calculus are not. Okay, and due to that reason Einstein theory become very much famous. Okay, so even if you are going to talk about the some kind of control system, some kind of mathematical modeling that is based on quantum, you are able to apply this kind of modeling principle. Okay, so with this remark, now lecture is in from my side. So if you have any confusion, then please let me know. Okay, if you don't have any confusion, then I am going to close the today's lecture.